usually normally starts. I'm going to start. So, all right. It's 8:30. Yes. Should we wait like 2 minutes more? No. Okay. So good morning, everyone. I'm Shayon. I'm a second-year PhD student in material science. Now, this presentation has twofold purpose. The first purpose being like I took the Sheridan Center teaching program certificate 1 last semester, which kind of involves, like, requires me to undergo this teaching something. Basically, I need to instruct for a short period of time to a class, which would therefore qualify me to get the certificate 1. Thus, here we are. Thanks for Babak, Melissa, and Charlie for being here this early morning, filming this. Oh, and by the way, you're going to get filmed over here, so if you're not wearing your best dress today, bad luck. However, we do have a video waiver, so in case you are like uncomfortable with seeing yourself on the screen, this is the time to raise your hand and say if you have any doubts. I guess the guys will be courteous enough to trying not to put you in the forefront, but we do need you to sign this video waiver. So I'm going to pass this on, just sign it, and then pass it back to me at the end of the class. Alright, so with all the formalities done now, so the presentation would talk about a very particular kind of modeling technique, which is known as the phase field model. Now, what happens in that? Let's take a physical situation where you have, guys, can you see this part of the screen? It's not really important, but can you at least see what I'm drawing? If I draw something like this, it's just a box with a line. So say this part you have is ice, and this part is water, and we're trying to simulate the very famous melting problem. Now the problem with such a system is that as the ice melts, this boundary here, the separating the ice and the water, keeps moving. Now all such problems in physics are known as moving boundary problem, where you have to explicitly track this boundary in order to apply the boundary conditions that are there in your system. Now, doing it in a computer, one of the basic disadvantage is computers are really bad when it comes to simulating discontinuities. For example, like if this is a function, just take any physical constant, for example, the specific heat. Now, as we move from here in the ice, they will have a certain value of specific heat for ice, and then it will suddenly spike and change into the specific heat of water. Now, a better way of modeling, or easier for the computer, would be that instead of a discontinuous thing, we have a smooth curve which kind of goes from the bottom, like instead of the sharp peak, smoothens out and then goes into the water eventually, in this fashion, instead of the discontinuous one. This technique is what is known as a phase field, where to each phase here, where in this case is ice and water, you allot a particular variable, say c or phi, which is known as the order parameter in a most general case, and then just say that, well, if the value of phi at a particular region is 0, then we say, well, that portion is ice. Or if it is water, then we say that's 1. And the interface, instead of a sharp interface here, we have what we know as a diffused interface, where instead of just a particular coordinate, it ranges from, the interface is defined as that area where there's a gradual progression of this term order parameter from phase A to phase B, that is from 0 here to 1. So, and so in this region, the value of phi would go from like 0, 0.1, 0.7 till it reaches 1. So that's pretty much it. Now, this phase field model is used to simulate a lot of physical manifestations, for example, crack growth. But in this particular course, this particular lecture, we'll be talking about an aspect of material science, which I'm majoring in. And as we go through, you're going to know how is this field applied. Now, the fun thing is, while we do this, like this entire set of modeling, so we first make the energy functional, and then we use some numerical scheme to kind of solve it numerically on the computer. And while we go through it, we'll be covering a lot of math topics, incidentally, which are covered in this particular course, and hence I'm here. So the first topic that we're covering is calculus of variations. So how many of you over here like at least know what a calculus of, or rather do not know what calculus of variations is at all? Like, anyone? All right. So what it does is, now say we have a function f of x and y, and we are wanting to minimize the function. So it's a function of multiple parameters. So if you have a function of multiple parameters, f of x comma y, the way to minimize this in general is you do the partial derivative of del f and del x equals 0, and then del f and del y equals 0, and then you solve it to find what's the minimum of that function. Now in certain cases, as you can see here in the part in red, there's something called a functional. Now what is a functional? In simple words, it is a function of a function. For example, in this case, x and y were basically independent of each other. But say in this particular function, x, y, and we also need the slope, we kind of know how, we kind of figure out that y depends on x. And to find the value of that function, we need not just x, but the value of y, and the slope of how the function depends. So depending on what y relates to x, we can have several different functions which can be put in here. And therefore the value of the integral will change on which function are we using. And our objective is to find the minimum, like the function y on x, which minimizes this entire integral. And the way to do it is an equation on your right, which is d dx or del f, del y, whatever that is. This is known as the Euler-Lagrangian equation. And if you solve this, you're going to find that function of y mapping to x, which gives you the minimum value of this integral. This can be made more clear if we do an example. Say, so say in a Cartesian coordinate space, you have 2 points, x and y, like x1, y1, and x2, y2. And our objective is to find the minimum distance between the 2 points, x1, y1, and x2, y2. Now, it can be this, and the length of this, the straight line, might be the minimum distance. But there can be infinite functions, like this is one function, or this can be another function. So the question is, what gives us the minimum distance? So to do that, let's create the functional. And so the objective, if we translate, whatever I said, if we translate in the language of math, we have to minimize this ds. Well, ds is a small incremental length between, like, from x, close to x1, say. It's a very small incremental length around here. Now we know that ds square is dx square plus dy square. Now if we take, so ds is dx times 1 plus dy dx whole square. Therefore ds would be square root of 1 plus y dash square dx. This is good. Now, are everyone clear on this bit? Cool. So, so this is the functional. This is basically f over here, which we got to minimize. Now, putting this in the Euler-Lagrange equation, what we get is del f del y prime straight there is equals to the differential of this functional with respect to y prime and ddx, which comes as square which is equal to a constant. We get this part. Now if we solve this equation, it kind of gives us the same thing where y dash, that is dy dx, is also a constant. Not this constant, but definitely some other constant. If you just work this out, it will boil down to this fact. And writing dy dx equals constant is, and if we solve this integral, we get y equals to ax, some constant, plus c. This is the equation of a straight line, which therefore tells that the shortest distance between any 2 points on a Cartesian plane would be the length of the straight line that can be drawn between these 2 points. Hence, this is an example of why calculus of variations is used, and how are we using it in the code will come later. Next is Lagrange multipliers. So what Lagrange multiplier does, again, it's a minimization problem, but instead of, we have a function f, and instead of finding the global minima of the function, we say that what's the minimum of that function provided certain other conditions are satisfied. For example, which are given by the constraint equations, and there can be more than one constraint equation, and the way you solve it is that you create a bigger function, f of x, plus some constant, scalar constant lambda, multiplied by the constraints. If you have more than one constraint, you would have more than one lambdas, and this can be solved, and the way you solve it is the same process again, like you take derivatives with respect to each independent variable, set that to 0, and you have n number of extra equations which are given by the constraint equations, and if you solve them simultaneously, you're going to get the values of x and y of the independent parameters, which when plugged into f gives us the minimum value of x satisfying the given constraints. Alright? Next where we go is Fourier transforms. I guess I would not, so this is a Fourier transform like any other mathematical transform such as Laplace. You plug in a function and it gives you another function. That's like the basic general of what a transform is. But the cool thing about Fourier transform is that you can do several nice things with it. In general, it's used in signal processing, but as I go through the presentation, we'll know that we're using this to use another nifty trick of Fourier transforms, which is to easily calculate derivatives. We're going to see that later. Next is linear algebra equation solving. Now, since computers cannot handle analytical functions, at the end of the day, we have to make our code in such a way that we get a series of linear equations, which we then plug to any numerical equation solving algorithm and get the answers. Eigenvalue problems, again, the statement is given by some transformation on a vector, which gives the same vector, except that it is scaled with a certain scalar form. And the last is finite difference method. Now what this does is, say you have a PDE, which is a differential equation, but as I said, computers can only solve numerical like linear equations. This is a technique to convert the PDE, or ODE, any partial or ordinary differential equation, to a discretized form, as they call it. Like, yeah, and then so this converts the PDE into a set of linear equations, which can then be solved using any numerical equation solving technique. Now, if you notice over here, there are certain paths which are given in red. Now, why so? Because for the purpose of this course, we really need not know how to solve the equation, like how to analytically or like by hand using a pen and paper solve the equation. We have computer routines which will do it for you, but what we should know is what we expect that code to give, and to get the right output, what is that input that we are to give to the particular code. So again, in all these cases, the inputs that are required is the one in in red. So, yeah. You guys want me to wait on this slide for a while we take notes or something?
I have a question.
Yeah.
Will these slides be made available to us after?
Yeah, I'll send it to Professor Peterson. So, now we are going into that very particular problem which we are trying to solve using all these techniques that I mentioned. And so before that, a brief insight into what material science does is that if you have taken any course in general thermodynamics, you would know that at the end of the day, the most stable form of any physical thing that you can see, that you see in the world, is so because that particular configuration, that particular form has the minimum energy. And so as engineers, what we try to do is that, say we want the system to be in a particular state, we engineer its composition and all of the parameters to such a way that the state of minimum energy is the state that we want. Now, energy is a very loose term because so by energy what I mean is that there is a function, some function, in this case let's call it G, which is a function of, in this case, the composition. And what is composition? For example, say we have brass, which is made out of copper and zinc. So how do we do it? How do we make brass? Is that we mix, say, certain percentage of copper and certain percentage of zinc, and then mix it all together, and that is known as brass. So the amount of copper we mix and the amount of zinc we mix, that value is known as the composition of that particular phase, which is brass. Now, this value is a function of the composition. Every system has its characteristic function, which is at a given fixed temperature and pressure, which is known as the Gibbs free energy of that function. And the most stable form that we can find in equilibrium is that particular composition. So that combination of like A's and B's over here, which gives you the minimum value of G. For example, if we see here, say C0, we are mixing like 0.4 A and 0.6 B because it's a fraction, so the sum always has to be 1. So 0.4% of A, 0.6 of B, and we find if we plug that into that function G, we have a value somewhere very high on that slope. But as I said, functions like the system will evolve in such a way that the overall G is minimized. So in this case, what would happen is, say we have an overall composition, a very homogeneous mixture of 0.4 A, 0.6 B. What will happen eventually is certain parts of the system will become rich in A. Over here you can see like there is more of A and less of B, and certain parts will become richer in B and lesser in A. So from an homogeneous composition of like, at each point in that space we have the equal amount, what you'll find is certain islands of A-rich area forming and certain zones in our system where there would be more of B. And why does it happen? Because then the net overall G, like, which will be given by this point, is lower, way lower than what it was initially. Is this clear? Like, why are we doing this? What's the objective of the free energy? See. Now, what do we want to do? So, as I said, G is a function of the composition. Our main target is to minimize it. And not just that, like, because if we minimize it, we know that what is the eventual equilibrium case, the condition of our system. But what we want to find is that, say we had initially given a composition which is all homogeneous, how, like, the way that homogeneous composition breaks down, the correct technical term here is phase separates into the system which leads us the most gives us the most minimum free energy. So that's what we want to follow, the kinetics of the system, how the elements rearrange themselves in such a way so that we get the minimum free energy. But in this case, why this is a challenging problem? Because if you do a very regular classroom thermodynamics, regular solution thing, what we find is this function g over here is the function of just x of the fractions of the composition, not at a point. So if you have a system like this, like a box, the value of g at any point will be directly correlated to the value of x or the composition at that point, not how that composition varies in the periphery of it. That is not happening. But in the most general case, what we want, like the function g is not just depend on the local composition, which is x, but also in local composition gradient, that is how that composition varies in the region around it. So let's construct that g functional, as I said. So if you see, this is the overall function. This part, the first part, is just depending on the value of x at each point. Like at the small dx, what is that value of x? However, over here, this term is creating all the problem because it's a gradient term. Like it also depends not just on the local value, but how that value changes around that particular point. And the last part, it might look similar, and it is, to a Lagrange multiplier, which is actually putting a constraint in it. And why do we put this constraint? Because if you remember the ice and water thing I showed, if it's cooling down, after some time the entire region will be just ice. So initially we had like order parameter over here was 0, over here it was 1. Now in this case, mind you, order parameter can be translated directly into the fraction, whatever, some function. And okay, coming back to this, it's 0 and it's 1. After some time where all the ice has cooled down, it will just be full phi equals 0. So the entire region will be just ice, which means in the entire system that we have, the value of that parameter will be 0 throughout. But in this case, because we're dealing with compositions, if some area gets, reduces in certain amount, the matter just can't vanish. That matter has to be conserved. So if there is some region which is getting rich in a particular composition, there has to be some other region which gets depleted with the same element. And the overall result is, although there would be distribution of, say, any particular species more in certain region and less in certain other area, the overall composition would be the same as we had first applied it, because matter cannot just go away or like get created on its own unless some chemical reactions go on, but this is not the case. This is where it's known as the NVT ensemble, kind of, where like the overall amount of material remains fixed. It just gets distributed in the areas of the system, but it remains fixed. So we do need to add this Lagrange multiplier over there. Now again, over here, this particular functional is like universally applicable. It is true for any material. But how do you know, how do you separate iron from nickel or copper from zinc? It is with these values of A and K, which are material constants, which uniquely identify the particular system that we are talking about. So for iron, there will be a different value of A and K, and you get the flow. Now let's try to solve it. Now, so the first step here is to figuring out the values of A's and K's, which I said is material constants. And to do material, like to figure out from very basic physics, how to, like what is those constants, we ultimately need to solve the Schrodinger equation, which is given by minus h bar squared 2m grad squared plus v. And if you compare that with ax equals lambda x, you will find that the Schrodinger's wave equation is an eigenvalue problem. So, and if we have a psi vector, which gives us, the psi square gives us the probability distribution. So psi is kind of a probability function. And if we can like map that Hamiltonian as a matrix, we can use eigenvalue solving techniques to figure out the value of what the psi's are, because in this case psi would be the eigenvectors of this matrix, which is known as the Hamiltonian. Clear on this? Okay. Now, life is not easy because the way, so for a system of, if psi is a n cross 1 vector, then you know that the Hamiltonian is n cross n, where n is the system size. So solving Schrodinger equation in a computer scales to the factor of n squared, which gets pretty big in a pretty short amount of time. So it's technically impossible and will take all the human's lifetime to solve the Schrodinger's wave equation exactly for one particular material. What do? Instead, we go to this thing called density functional theory, where the technique of solving is we guess, just not a wild guess, a calculated guess, which is close to original. We guess the value of the psi. Based on that, we construct the Hamiltonian. Then we take the matrix, that energy, we minimize it using algorithms such as, again, minimization algorithms such as gradient search, etc. And from that, with the minimum Hamiltonian that we get for that configuration, we calculate a psi, a new one. And then we keep doing it again and again and again, till the psi that we put in and the psi that we get out is same, barring a sudden marginal errors. And this entire technique is known as a density functional theory. There are popular packages which do it for you, known as VASP and Quantum Espresso. There is Gaussian and so whatnot. But at the end of the day, if you figure out psi for a particular system and you do some statistical averaging on that, we can get the values of A's and the K's that I talked about. So, alright, where are we now? We have this free energy functional. We have figured out what A and K's are. Nice. And then we have to apply the Euler-Lagrange equation. But before that, what we got to do is, as I said, we don't want to find what the minimum configuration is. We want to see how, from the initial configuration, the system reaches that bit. And the flow, the kinetics of the system is governed by a very, very general form of Fick's law, where the time derivative, the way the physical intuition for this equation is that, say you have a box, you have some things going in and some things coming out. The net accumulation or reduction of that material in that particular box with time would be the amount of matter going in subtracted by the amount of matter going out. So if you plug in 4, you get 2, you know that you have a net increase of 2 in the system, which in mathematical language can be described by Fick's law. Again over here, M for this particular case, because this is composition, is known as the diffusivity of the material, but it can be anything which kind of maps this law properly. Alright, so what do we need in this? We want to see how x changes with time. So for that we need to identify what is that function, the which minimizes the functional that I gave you. And I'll not do all the derivation of this. The derivation is known as the Kahn-Hilliard derivation of phase field, which is a seminal paper which I can forward with this mail. But for now, let's be happy with the fact that del f min del x is that particular function, where f is the free energy function that I previously drew. And likewise, k is our material properties, x is the composition, and likewise. Is everyone clear with this equation? Not the derivation, but what are the different parts of this equation are? F being that and the rest. putting this equation on top is, we're just expanding the Laplacian over there. So df dx is g over there. So if you pull the grad square in, it becomes minus m times del 2g del x2 minus 2k. Wait, oh, there's one mistake. I think I should have added a negative sign on top, which is missing. Like, it's del x del t equals minus m. But anyway, so where we are now, we get this final partial differential equation, which we have to solve using a computer. Now let's analyze this equation a little bit. So we have one differential in time, that is del x del t. We have one double differential in space, that is del 2g del x2, one fourth order differential in space. Now let me tell you that in most of these problems, g, which is defined as del f del x, is a simple equation. You know, it's mostly, if you see the homework problem later, it's of this form x into 1 minus x into 1 minus 2x, as I already gave. And it's a very simple function, which can easily be differentiated and integrated. So we are doing this analytically, at least in this problem, but the rest of the part will be done using a computer. Okay, so how do we solve them? Let's do it. So we have one time differential, two space differentials. Let's solve them one at a time. Dealing with the space derivatives, and that's where Fourier transforms come in. Now, one very neat trick about Fourier transform is that, say you have a function f of x, you do a Fourier transform of that, and you get a new function which is known as, let's say, call it the g cap of x. G cap of x is the Fourier transform of f of x. Now, if we multiply g of x with I, k, g of x, we get a new function where k is given by 2 pi x by L, technically known as a reciprocal space vector. Now, if we do an inverse Fourier transform of this, it's an inverse Fourier transform of I, k, g cap x, we get, let's say, another function which is m of x. The fun thing here is that m of x is nothing but dd this. So if we take a function, do the Fourier transform, multiply that with the ik at each point, and then inverse Fourier transform it again, the final function that we get will be the derivative of this initial fx that we are doing here. Which is, now, what I showed the example is just for the first derivative, but if you want to do like multiple derivatives, what you got to do is just as f of n, just multiply with I to the power n, k to the power n for each of the functions. So the double differential, if we want to find del 2f del x2, instead of this we need to multiply with like I square, which is minus 1, minus, and then k square. So again, f of x, Fourier transform to g of x, multiply with minus k square, inverted Fourier transform, which gives you a new function which is nothing but the double derivative of the initial function f of x that we had put in. Right? I guess I got the proof of that. Is anyone like, are you convinced with this, or do you not believe me? Because then I can show you the derivation of this. It's pretty small, but if no, I will suggest that we skip it now, and in case you're interested, we can come back to it later. I'll show you how this works out. But so we did this. We take all our functions to the Fourier space, and the same PDE that we obtained in the previous case, after a Fourier transform all of its elements, the new differential equation that we have to solve turns out to be this. Let me just write this down here so that we can compare. What we have is del x del t is this is the function, like this is the PDE. In the Fourier space, this remains in the after each of these things have been transformed in the Fourier space. We have M. So del 2f del x2 becomes G. So k squared G, and this becomes minus 2 capital K small k to the power 4 and x. Clear of how this transformation works out and how by using Fourier techniques we have like eradicated the space derivatives. We have like done with the space derivatives, because if we do that, what we get is from a PDE. Now this is nothing but an ODE. We have reduced one level of complexity by removing two space derivatives here. Any questions? All right. The next step is discretization by using finite elements, finite difference. Can you guys see this equation here, right? Okay. So let's do a small derivation. I guess finite difference hasn't been covered in this class, right? Has it? Okay. So say you have a, for example, you have a system of, you have a 2D function in a box. So you have a function u which depends on x comma y. Now if we expand the function in its Taylor series, you have u of x plus h comma y. So you're just moving along the x direction and we're expanding the function around h. We have around x, we have u of x plus h. So this thing ux is like del u del x plus half x squared u xx is the double derivative plus higher order terms. Like this is expanding the function around x, keeping y constant in its Taylor form. And if we do it the other way around, x minus h comma y, we have the same thing, kind of. We have minus h mu x plus, because this is second term, and higher order terms. Now from this, if we subtract, if we neglect the higher order terms and you subtract this equation, what we get is ux comma y will roughly be equal to 1 by 2h if we see this equation, what we get is, assuming h over here, that is how far are we moving from the point of interest, is very small, the derivative of the function u of x at that point is roughly equal to 1 by 2h, whatever space you're considering. So for example, say in a 2D we want the function over here, x, and we know that the value of the function around here, like slightly high, h is x plus h, and this side we need the function here, x. This is x plus h, and this is x minus h. We can find the value of the derivative of the function at this point if we know the values, the exact values of the function at a length like plus h and minus h on each side. We can kind of approximate what the value is of the derivative. The same can go for the y component, which will be given almost equal to 1 by 2k over here, because now in the previous case we moved in the x direction, now we're moving in the y direction, and the gap need not be the same. So just for the sake of completeness, taking a different term, we'll give that x is common, y plus, x remains the same because we're keeping x constant. This is uy, so this is the derivative, like the partial derivative with respect to y. And if we just go along with this, we can also find the double derivatives of the function, which will be given as uxx and uyy would be just, let's just write it down. Right. So this is known as a finite difference scheme, where what we do is, instead of, in a system, instead of having the values continuously, we only are interested values at certain points of the function. So instead of a continuous, we are having like discretized steps, hence this step is known as discretization. We calculate the values at discrete points in the space, and at that point, the derivatives can be approximated to a good extent by using these formulas. There are other ways of doing it. One, like most common one is finite element, which also aims at solving ODEs and PDEs by using the discretization step. But yeah. So if everyone has like got this jotted down, I'd like to get the screen back down again. Right. So based on what I said, the del x del t is written as in this form from over there. Now a thing to note here is that this is a problem where we have, although we have dealt with the space derivatives, ideally if we had done the entire thing in the real space, we would have had a delta t, like how much are we moving it in the t, which is known as time step, and then we have the space step, which is delta x. Now you might guess that the smaller the h I take, the smaller the jump I do in my domain, the better should my results be. However, there is, for the sake of these methods may not always converge, that if you solve it in this way, you might get nonsensical values. And for that, just be careful. So all that you have to read, if you're interested here, is finite difference schemes. And there are several schemes goes by the name of semi-implicit, implicit, explicit, and each of them have its own convergence criteria, which is to be known if you want to code it in any other form. In this particular case, the scheme that I've employed is known as the semi-implicit finite difference scheme, again, to be noted. And before we go to the results of that, because this, so far we are done, because we know what to solve. This is nothing but a linear equation, which can now be plugged into a computer to be solved. But you might say that this is just one equation. Why do we need to solve like a simultaneous set of equations? Because in the most general case now, x need not be a scalar. It need not be a value at that point. For example, what I told you was two components, like a and b. And I also told you that the a and the b have to sum to 1. So if we just solve for one variable, we basically solve for 2, because the value of the other one would be 1 minus the value of this. But what if we have 3 variables? So we are mixing like some amount of copper, some amount of zinc, and we're adding to the mix some amount of molybdenum. So in the most general case, x is going to be a vector of all the terms that we are solving. So composition of A, B, C. There can be, there's another one thing that I'll mention when I show the results. But if these are vectors, then k's and m's would be in general matrices. If these are, so if you have like n comma 1 vector, like each point is identified by a set of n values, the material constants would be a matrix of n cross n. Therefore, this in the most general case qualifies as a vector equation, which is like a set of n different linear equations that can then be solved using any numerical technique. Right? Okay, so let's note down this equation, because now we are going to solve, like I'm going to discuss how to code it, like how to translate all the steps that I mentioned into a code which does the thing. And the last bit is particularly important because, as Professor Peterson said, there's going to be a much simpler version of this, but an assignment problems where we'll be asked to code this very thing and get the answers. So first we need to know, okay, well, before that, like what are the criteria